In this video, I would like to go over another feature of gravitation, which is summarized in Kepler's laws. All right, so for a little bit of historical background, there was a Danish astronomer named Tycho Brahe, spelled like this. And this is one of the historical figures who's often referred to by his first name, so people will call him Tycho, and everyone knows who you're talking about. And he was a really peculiar person. He was this noble and was very vain and stuff. And there's a lot of weird stories about his life. But one of the things that he chose to do is he would go out every night and just collect a ton of information about the positions of stars in the sky. He didn't have a telescope. He just went out and made, by eye, as precise of observations as he could. And he did this for something like 30 years. I'm not sure the exact amount of time. But he didn't really have a plan for this data. He just kept on collecting data for a long time until he died. And so, following his death, one of his students, Johannes Kepler, inherited all of this data. So he took, these decades worth of astronomical observations, and he analyzed them. Okay, so Tycho collected all this data, and Kepler did the analysis. And from all of that data, Kepler came up with 3 laws of planetary motion. Okay, so Tycho was collecting positions for Mars and Mercury and Venus and so on. And Kepler's 3 laws of planetary motion were just simply based on that data. So there was no physics behind it. There was no model, no reason to think that these should be true. Just a bunch of data that indicated that these 3 rules were true. And to set the stage for this was after Copernicus, so people knew that the planets were orbiting the sun. But they thought that the planets orbited the sun in circular orbits, and that they had all these different ideas. And so Kepler's first law is that, in fact, planets follow elliptical orbits. All right, so as opposed to circular orbits. Elliptical orbits are a little more complicated than circular orbits, but this is what he saw, that planets were following orbits of that shape. Kepler's second law is that planets sweep out equal areas in equal times. Okay, so that's a kind of peculiar rule, and I'll talk more about that in a moment. Kepler's third law is that the period, which is to say the year of a planet, t, is proportional to the radius of its orbit to the 3/2 power. Okay, so there's a little bit of a detail here because I told you that the planets follow elliptical orbits rather than circular orbits. So what does the radius mean? It turns out that's the semi-major axis of the ellipse. So if you have studied ellipses, then you know what that is. But it's basically the longest radius that you could draw for an ellipse. Okay, so let's talk about these laws one at a time. In particular, through the lens of Newton's law of universal gravitation. Because Newton's law of universal gravitation is one rule that implies all 3 of these. So one way that you can tell you've got a really good physical law is if you can use that law to explain multiple things that seemed separate otherwise. So I already described how Newton's law of universal gravitation connects the everyday phenomenon of objects falling to the ground with the motion of astronomical objects. So that already has combined two different phenomena into one uniform, phenomenon. Well, Newton's law of universal gravitation also explains Kepler's three laws of planetary motion. Okay, so starting out with the first one, the ellipses, it's actually really hard to show this. So the ellipses, I'm going to just kind of glide past. So it is possible to show that Newton's law of universal gravitation implies elliptical orbits. Newton claimed that he showed this, but it's not clear whether he ever actually derived it. He might have just been bragging. But today you can look it up, and like I said, the derivations are pretty complicated, but it is in fact true. Okay, so the second law is, I think, a little more interesting. It turns out that this equal areas law is basically just a statement of conservation of angular momentum. Okay, so let me sketch an ellipse like this. And let's say that the sun is over here. Okay, so the sun is at one focus of the ellipse, which is not in the center. Okay, so that's, kind of a mathematical detail. If you've studied ellipses, then you know what a focus of an ellipse is. If you haven't, then I'm not going to, teach it to you today. But you can always look it up on Wikipedia if you're interested. Okay, so the idea here is that if you consider how far a planet goes in, let's say, a day, well, it's going to move from some position to some other position. Okay, and that little triangle that I drew has some area, and the claim that the planets sweep out equal areas in equal times is that if I picked some other point in the orbit, let's say here, then in that same amount of time, one day, then the planet would have swept out the same area. Okay, so the claim is that those two areas should be the same if the same amount of time has passed for that planet. Okay, so what that means is that the planet is going fast when it is closest to the sun, and it is going slow when it is furthest. Okay, so it turns out that this is just conservation of angular momentum. Which is not very difficult to derive, but I'm not going to actually derive it. If you wanted to do it, what you would do is define the radius vector. So there's r, there's the velocity vector up there, and then using some math, you would relate the area, r and v, and then remembering that angular momentum equals r cross p. Well, p is m times v. So r and v show up in both of those expressions, and you can figure out that the area swept out is just proportional to the angular momentum. Okay, so then the one I really want to focus on is the third law, because we can actually show this pretty easily with what we have seen before. So the claim is that t is proportional to r to the 3/2. All right, so let's show this with Newton's law of universal gravitation. So the law says that the force on a planet by the sun is equal to g times mass of the sun times mass of the planet over the radius. We'll just assume a circular orbit to make this easier, but it still works with an elliptical orbit. It's just a little harder to show. Okay. Well, so the force on a planet is going to be equal to its mass times acceleration. So mass of the planet times the acceleration of the planet. And notice that I have two different places here where the mass of the planet shows up. So I can cancel those out, and I get g times the mass of the sun over r is equal to the acceleration of the planet. But if the planet is in circular motion, then that's going to be equal to v squared over r. Oh goodness, I forgot to do r squared for each of these. Okay, sorry. Newton's law of universal gravitation has a squared. Okay, so at this point, I have r's on both sides of the equation, so I can cancel some of those out. So just simplifying a little bit, g times mass of the sun over r equals v squared. Okay, well, the speed of the planet is equal to the path that it follows, the circumference, 2 pi times the radius, over the time it takes to complete that circle. Okay, so that's just the distance over time, essentially. So if I plug that in here, then I get g times mass of the sun over r equals 2 pi r over t squared. Okay, and what I'm going to do is I'm going to solve for t. So I'll move the t's up to the left, and I get t squared equals 2 pi all squared over g times mass of the sun r cubed. Okay, so just rearranging algebraically. And then finally, if I solve for t, then I get the period, or the year, is equal to 2 pi over square root of g times mass of the sun times r to the 3/2. Okay, so not only can we show that the period is proportional to the radius to the 3/2 power, we can even find what is the constant of proportionality. Okay, so this is a great success of Newton's law of universal gravitation.